Let's look at diastereomers. So diastereomers are stereoisomers, meaning they have the same bonds and the same connectivity, but they're not mirror images of each other. If you remember enantiomers, these are two stereoisomers that are non-superimposable mirror images of each other. Diastereomers are stereoisomers that aren't mirror images. So if we take this first compound, we know we can draw its enantiomer by either reflecting it across the y-axis or just flipping our wedges and our dashes in our chiral carbons. But for diastereomers, we're going to do something a little differently. All we have to do is leave at least one of our chiral carbons how they are. So we just need to flip at least one chiral center. So if we look at this compound, we can draw a diastereomer by flipping this chlorine and leaving the bromine group as is. This is a diastereomer. They're stereoisomers because it's the exact same connectivity. All the carbons are attached to every other group that's here, but they differ in their spatial arrangement, and it's not a reflection across the y-axis from our original molecule. We can draw another diastereomer by leaving the chlorine this time and flipping the bromine. Either one of these are diastereomers to the original, and they are also enantiomers to each other. This chlorine is wedged and the other is dashed. This bromine is wedged, the other is dashed. If you remember enantiomers, if you flip all of our chiral carbons, then we're going to have enantiomers. But if you're only flipping one, you're going to have diastereomers. Now this isn't going to be the case for everything. It just happened because we drew multiple diastereomers. They happen to be enantiomers. But diastereomers are essentially created by just flipping at least one of the chiral carbons. So if we look at our configurations, if we have R and R, and we compare it to S and S, these are going to be enantiomers. If we have R and R, and now we have R and S, these are diastereomers. Why is that? Because we still save one of our chiral carbons, but the other one is different. Whereas in our first example, we have two R's, now they're two S's. We flipped all of our chiral carbons, so they're enantiomers. If we look at another combination, if we have R and S, and we go to SR, what are these? These ones are also enantiomers because our R turned to an S, our S turned into an R. All of our chiral carbons here have been flipped. So diastereomers, we're going to maintain at least one chiral carbon, and then we can switch any other chiral carbon.